Welcome, fellow AI enthusiasts. Have you ever wondered how large language models like GPT-3 understand and process text? The secret lies in a fundamental component called a tokenizer. Today, we're going to demystify this process by building a byte pair encoding, or BPE, tokenizer completely from scratch. This isn't just an academic exercise. Understanding tokenizers is crucial for anyone working with modern NLP models, from data scientists to ML engineers. By the end of this lesson, you'll have a clear step-by-step guide to creating your own functional tokenizer, a core piece of technology powering the AI revolution. To follow along, you'll need Python 3.8 or newer and a basic understanding of machine learning and natural language processing concepts. The coding portion of this tutorial is designed to be completed in approximately 1 to 2 hours, giving you a powerful, hands-on learning experience. Let's get started and build something truly foundational. Our journey begins at the most granular level, bytes. Every modern tokenizer starts by converting raw text into a sequence of UTF-8 bytes. Think of it as breaking down your text into its smallest fundamental units, each represented by a number between 0 and 255. This initial step gives us a vocabulary of 256 unique byte tokens. The core idea behind byte pair encoding is to then compress this byte sequence by merging frequently occurring adjacent pairs. So, our next step is to meticulously count how often each pair of consecutive tokens appears in our training corpus. This statistical analysis helps us identify the hottest pairs, those that appear most frequently, because merging them will yield the greatest compression and create more meaningful, longer tokens. Once we know the most common pair, we're ready to make our first merge, effectively expanding our vocabulary beyond the initial 256 bytes. With the foundation laid, we move into the heart of the BP algorithm, training. This is an iterative process where we repeatedly count the most frequent adjacent byte pairs and merge them into new, single tokens. We continue this merging process until our vocabulary reaches a predefined size, perhaps 50,000 tokens, gradually building up complex words and subword units from the initial bytes. Once trained, our tokenizer is ready to encode new text. We apply the exact same sequence of merges learned during training, greedily replacing any recognized pairs with their new merged token ID. The reverse process, decoding, is wonderfully straightforward. We simply concatenate the byte sequences corresponding to each token ID and convert them back to human-readable UTF-8 text. Finally, to ensure our tokenizer is working correctly, we perform a crucial round-trip test. Encode some text, then decode it, and assert that the decoded text is identical to the original. This guarantees consistency and accuracy. While our basic BPE tokenizer is functional, real-world applications demand a few key enhancements. First, we introduce regex chunking, REGEX chunking, before applying merges. This means splitting the text into meaningful chunks, perhaps by spaces, punctuation, or numbers, before BPE, preventing awkward merges like dog becoming a single token and improving token boundaries. Next, modern LLMs rely on special tokens, such as end of text to mark the end of a document, or pad for padding sequences. These are assigned unique IDs after training and are never subject to the merging process. For practical use, you'll need to save your tokenizer's artifacts, the vocabulary mapping, token IDs to bytes, and the ordered list of merges, so it can be loaded and reused without retraining. Finally, always consider your corpus choice. Training on text relevant to your target domain will yield a much more effective tokenizer. And for large-scale applications, while Python is great for prototyping, you might need high-performance implementations in languages like Rust. Congratulations! You've just walked through the fundamental steps of building a functional byte pair encoding tokenizer from scratch. This is the very same foundation used in many state-of-the-art large language models, including OpenAI's GPT series. You now understand how raw text is transformed into a sequence of numerical tokens that an AI model can process, and how those tokens can be efficiently compressed and then decoded back to human-readable language. This knowledge is invaluable for debugging, customizing, and truly understanding the behavior of modern NLP systems. As a next step, I encourage you to experiment. Try training your tokenizer on different text corpora, perhaps code, social media data, or scientific papers, and observe how the learned vocabulary adapts. Also, play with different vocabulary sizes and explore how they impact the length of your token sequences and the overall efficiency. Finally, delve into other advanced tokenization strategies like word piece or sentence piece, which build upon BPE principles to offer even more sophisticated text processing capabilities. Your journey into the heart of AI has just begun.